Hello everyone, welcome to Ekeeda platform, and this is Jangid here, your electrical faculty. And in this video, I'm going to talk about the single tuned filter, and which is a type of your passive filters. So let's start with some of the points which I have included, so that these can be justified to your single tune filter. So I will start with the single tune filter can be represented as follows, having the omega r is equal to 1 upon root LC. And that is a kind of the resonance frequency. That is a kind of resonance frequency you have to remember. If I talk about the designing of the filters or the basic representation diagram of that, then we can use this type of diagram, having the capacitors, inductor, and this resistor block. Okay, and this point consider, let us consider A, and this point is considered, let us B. So all the capacitors, inductor, and the resistor all are connected in series with each other, such that if I find their x naught or reactance value, that is going to be omega r L. If I talk about for the capacitor, then it will be 1 upon omega r C, and this is ultimately is going to be root L by C. This is your representation for the totality. So if I talk about the x naught, so x naught is having the three formulas, which are omega rl plus 1 upon omega rc and the root L by C. So reactance of the inductor and the capacitor at the resonance frequency, these are the reactance. This is the reactance of the inductor, this is the reactance of the capacitor. Okay, so how because we generally use 2 pi fl for representation of xl. This is a 1 upon 2 pi fc. Okay, so that is the xl, this is the xc, but we are talking about at the resonance frequency, so we are taking the omega r here, and this is the reactance of the inductor and the capacitor at the resonance frequency. At which frequency? Resonance frequency. Now let's talk about the impedance of the single tuned filter. Which type of filter? That is the single tuned filter. So if we talk about the single tuned filter, then we are having this type of relation. That is given to us. That is, please read this because this is going to be important one. If we talk about, one second, if we talk about ZFH, ZFH is for the filter, F for the filter, ZFH, H for the harmonics, and this is R plus J H omega L minus 1 upon H omega C. Whatever we have talked about in the resonance, okay, in our network analysis, the same way we have to talk about, but we have just multiplied value of H, the variable H. So what are the different variables here? R, L, and C, you already know what are that. But if you talk about the omega, here the omega is a fundamental frequency of the system, which system we are actually using. If we talk about this H, whatever the multiplied here and it is multiplied here, that H is kind of the order of harmonics. That is order of harmonics, which let us suppose we have taken the 11th harmonic we are going to find, then H is actually going to be 11. So here we will write 11 omega L minus 1 upon 11 omega C. Let us take, we have taken the 23 for the 12 pulse converter. Okay, then we will multiply 23 omega L minus 1 upon 23 omega C. Now if we talk about these tune filters, is actually designed to filter a single harmonic of order HR, and that is actually representation. HR omega is kind of omega R. Omega R we have discussed, that is a resonance frequency, and that is actually HR omega. Now, so if we talk about the variations of the ZFH upon X naught with the function of H upon HR, then this kind of curve we will see here. Okay, this is the variation. This x-axis is representing H by HR ratio, and this ratio is actually represented by the y-axis. Which axis? That is the y-axis is representing, that is a ZPF upon X naught. So this going to be at a value of 1 when the H by HR, both the values are actually equal, then the ratio is going to be 1. Then what will happen? The curve will come to slightly and steeply it will decrease. And after the value of 1, when the value of h is going to be more as compared to the HRU, more than the resonance frequency, then it is kind of increasing curve. Okay, but before the h upon hr, it means h is less as compared to the hr. That's why we are getting the ratio from 0 to 1. That value will be positive, but it will be less than 1. That's why we are getting, and this portion is for when h is less than hr, and this portion is for h is greater than hr. Okay guys, now so this curve is going to be like that. Up to 1 it will decrease, and after the 1, when h is more than the hr, it will increase, kind of increasing type. Now, so what we are doing here, the variation of h, so h is whatever is written is viewed as a continuous variable. That is actually the continuous variable what we are using. Now, it is actually necessary to compute the impedance of, if we're talking about the tuned filters, as a function of detuning a parameter. So we can also, as in the resonance we were using the delta, that was a ratio for the frequencies. Okay, so change in the frequency divided by the resonance frequency. We were actually using the resonance chapter in your network analysis. The same thing we are going to do here. If you're talking about the delta, that is the detuning, that is actually the detuning parameter. What is that? Please start, I'm marking a star, so please remember this. This is called the detuning parameter, and this detuning parameter is same way as representation as we were using in resonance chapter. So what its value? Its value you have to remember and memorize, that hr omega minus omega r upon hr omega n. So when you will divide separately, then you are going to get omega upon omega naught minus omega r upon hr omega n. This value you are going to get. And or this can also be represented as delta is equal to 1 plus delta f upon fn minus 1 plus del L upon ln into 1 plus del c upon cn, and whole is equal to minus 1 by root 2. I have corrected it. Okay, that is minus 1 by 2. It means 1 upon root of this. After the simplification, you have to use the binomial kind of equation. Then you are going to get delta is equal to delta f upon fn plus 1 by 2 delta L upon ln 1 by 2 delta c upon 2 cn. This thing you are going to get, where delta L and delta c is the change in the inductor and the change in the capacitor value. But if we talk about the ln and cn, then these ln and cn are going to be, this ln and cn are the nominal values of the inductor and the capacitors, such that hr, if we talk about the hr omega n, if we talk about the hr omega is omega, if we talk about the hr omega n, then it is kind of 1 upon root LC. But here we will write nominal values of inductor, that is ln, nominal values of the capacitor, that is Cn. Now, so this curve we have discussed. Now, after the simplification, we can also get r plus jx naught. How you are going to get? Just multiply and divide by x naught. You are getting the simplification of this, where the x naught is actually hr omega ln. Okay, and second value is your 1 upon hr omega n cn. So what you have to do, this right portion, this right side portion, it means it value is going to be comparable with this. So what we are doing, we are taking the imaginary value of this and equating to this equation. After the equating to this equation, and after the manipulation and calculation, simple manipulation and calculation, you are going to get this value. That is kind of 2 delta f upon fn plus del L upon ln plus del c upon cn. Okay guys, now r plus j x naught 2 delta x naught 2 delta. So What is that? Because the delta we have found in this one is kind of same, but just you have to multiply by 2, then you are going getting 2 delta, and we are taking the common x naught. If you are taking the common x naught, it will be r upon x naught, that will be actually a q inverse. Okay, and here it will be plus 2j delta. I hope you have understood related with the single tuned filters. So tata bye bye and thank you.